Lesson 6. Introduction to Motors. Contents. The topics covered in this lesson are DC motors, brushed and brushless, pulse width modulation, PWM, servo motors, motor control commands. The tasks and/or activities for this lesson include motor control. Actuator. An actuator is a component that is responsible for moving and controlling a mechanism or system. An example of an actuator is an electric recliner, which has motors inside that are actuated through a user interface, that is often a button. Other examples include office chairs that have pneumatic cylinders for height adjustment. Valves used to control the flow in a pipe could also be controlled using an actuator. Motors are one of the most common actuators that can be controlled using a microcontroller. Types of actuators. There are various types of actuators that operate on different working principles such as hydraulic actuators, pneumatic actuators, etc. There are different types of electric motors as well, such as DC motor, servo motor, stepper motor, etc. However, the focus of this lesson is DC motors and servos. Electric motor. An electric motor is an electrical machine that converts electrical energy into mechanical energy. An electric generator does the opposite. It converts mechanical energy into electrical energy. The animation on the right shows the working of a motor and generator in theory. However, the working principle and construction of these devices is not as simple. Electric motor working principle. The DC motor works on the principle of Lorentz law, which states that a current-carrying conductor placed in a magnetic field experiences a mechanical force. The direction of this force is given by Fleming's right-hand rule. As it can be seen in the image on left, the right hand is held with the thumb, first finger and second finger mutually perpendicular to each other, at right angles. The thumb is pointed in the direction of the motion of the conductor relative to the magnetic field. The first finger or forefinger is pointed in the direction of the magnetic field, north to south, and the second finger or middle finger represents the direction of the induced or generated current within the conductor, from the terminal with lower electric potential to the terminal with higher electric potential, as in a voltage source. The animation on the right can help paint a clearer picture of the working of a DC motor. Working of a DC motor. The following video explains the construction and working of a brushed DC motor.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But, if you observe the torque action on the coil closely, you will notice that, when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor, if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation.
To summarize, the DC motor has a stator, which provides constant magnetic fields, a rotating armature, called rotor, which is a simple coil connected to a power source through a pair of commutator rings. The commutator is a rotary switch which reverses the current directions, without losing contact. When power is turned on, and current flows through the coil, an electric force is induced on it and according to Lorentz law, so the coil starts to rotate. As the coil rotates, the commutator ring rotates, and since it is connected to the power source of opposite polarity, left side the electricity will always flow away from the source, and on the right side, electricity flow towards the source. This ensures that the torque action is maintained in the same direction. If you observe the torque action closely, you will notice that when the coil is perpendicular, the torque is less, which creates an irregular motion of the rotor. To overcome this, one more loop can be added, with separate commutator arrangement, so that when the first loop is vertical, the second loop is connected to power source and there is a constant and stable motion. As more such loops are added, the rotation will get smoother. Brushed versus brushless DC motors. In the previous slide, the working of a brushed DC motor was described. What about a brushless DC motor? The name is self-explanatory. A brushless DC motor does not have any brushes. But also, it has permanent magnets for the outer rotor and rotating coils for the inner stator, unlike brushed DC motors that have permanent magnets for outer stator and rotating coils for inner rotor. The advantage of brushless DC motor is that there is no chance of sparking due to the wear of contact brushes that are made of metal. It is also less noisy and has a longer life. DC motor direction control, half bridge. How to control the direction of rotation of a DC motor. An H-bridge is an electronic circuit that enables a voltage to be applied across a load in opposite directions. These circuits are often used in robotics and other applications to control a DC motor to run clockwise or counterclockwise. Most DC to AC converters, power inverters, AC converters, DC to DC push-pull converter, motor controllers, and many other power electronics use H-bridge circuits. A half-bridge circuit consists of two switches, two batteries or power sources and a DC motor, circuit shown in the diagram. A half-bridge cannot switch the polarity of the voltage and hence require two power sources. Half-bridge circuit using switches. When SW1 is closed, B1 is connected to the motor, current flows from left to right, motor turns in one direction. When SW2 is closed, B2 is connected to the motor, current flows from right to left, motor turns in the opposite direction. SW1 and SW2 cannot be closed simultaneously, as this leads to B1 and B2 being in short circuit. Half-bridge circuit using transistors. Recall that a transistor can work as an electronic switch, and hence, it can replace the mechanical switch in the bridge circuit. Consider the circuit shown with switches replaced by two NPN transistors for electrical switching. Case 1. IN1 is high, Q1 conducts and so, the motor turns in forward direction by B1. Case 2. IN2 is high, Q2 conducts and so, the motor turns in reverse direction by B2. IN1 and IN2 cannot be driven high simultaneously, as this leads to B1 and B2 being in short circuit. The main disadvantage of a half-bridge DC motor drive circuit is that it requires a dual power supply. Note: these circuit diagrams are for conceptual understanding only. Diodes will be required in the half-bridge circuit for control of a DC motor in real life. DC motor direction control using a full bridge. A full bridge circuit is called a H-bridge. The shape of the circuit resembles the letter H. Consider the circuit show, which consists of 4 switches, 1 voltage source, and a DC motor. Case 1. SW1 and SW4 are closed, SW2 and SW3 open. So VCC drives motor in forward direction. Case 2. SW2 and SW3 are closed, SW1 and SW4 open. So, VCC drives motor in reverse direction. Note: these circuit diagrams are for conceptual understanding only. Diodes will be required in the H-bridge circuit for control of a DC motor in real life. H-bridge circuit, using switches. This is an animation to paint as clearer picture of how a H-bridge is used to control the direction of a DC motor. Note: these circuit diagrams are for conceptual understanding only. Diodes will be required in the H-bridge circuit for control of a DC motor in real life. H-bridge circuit using transistors. Consider the circuit shown with switches replaced by 2 transistors for electrical switching. The working remains the same. Note: these circuit diagrams are for conceptual understanding only. Diodes will be required in the H-bridge circuit for control of a DC motor in real life. DC motor direction control, H-bridge. To control a DC motor in real life, the full-fledged H-bridge circuit in Figure 1 can be used. How this full-fledged H-bridge circuit using transistors and diodes circuit 1 works. High signal enters QA, which turns on transistors Q1 and Q4. Current flows from positive supply terminal through the motor from left to right, forward. To reverse the direction, remove high signal from QA, and apply to QB instead, which turns on transistors Q2 and Q3. Diodes are used to prevent damage to switching elements from inductive kickback. Why is diode required in a H-bridge? In any of the operation cases, forward, reverse, on each side of the H-bridge only one switching element, that is, a switch or transistor, is on, to allow current flow across the motor. Turning on both switching elements on one side of the bridge will create a short circuit. Although this is avoided in a real circuit, momentary short circuit is unavoidable while switching from forward to reverse condition. That is, it is not possible to exactly turn on, off different switching elements exactly at the same time, and it takes some time for the voltage to drop across the switching element. On the contrary, turning off both switching elements on one side, the motor, inductor, voltage will jump high enough to create a path for current flow by damaging the switching element to create a short circuit. The diodes provide a short circuit path, dissipating this energy as heat. Please note that the switching elements here refer to transistors or relays. L293DIC for DC motor direction control. Motor driver ICs are integrated circuit chips that simplify control of motors. The L293D is a 16-pin motor driver IC which can control 2 DC motors simultaneously and independently. It can provide 600 mA per channel at a supply voltage range of 4.5 volts to 36 volts. It has an internally embedded diode, so there is no need of external diodes for interfacing the DC motor. The IC consists of 2 bridge circuits inside, and its pin diagram is shown on the right. Activity 1. DC motor direction control. Wiring Arduino with L293D and DC motor. Pause the video here to do this activity and hit play when you are done. Activity 1. DC motor direction control. Code. As it can be seen, 3 variables IN1, IN2, and EN1 are declared as integers to represent pins 11, 10, and 9 on the Arduino, which are connected to the IN1, IN2, and N1 respectively. In the setup, these pins are set to output mode, and the enable pin is set high using digital write command. In the loop, IN1 is set low, and IN2 is set high for 3 seconds, that is, 3000 ms using the delay command, and then IN1 is set high and IN2 is set low, changing the direction of current through the motor, and consequently the rotation direction of the motor. Activity 1. DC motor direction control. Code. As it can be seen, 3 variables IN1, IN2, and EN1 are declared as integers to represent pins 11, 10, and 9 on the Arduino, which are connected to the IN1, IN2, and N1 respectively. In the setup, these pins are set to output mode, and the enable pin is set high using digital write command. In the loop, IN1 is set low, and IN2 is set high for 3 seconds, that is, 3000 milliseconds using the delay command, and then IN1 is set high and IN2 is set low, changing the direction of current through the motor, and consequently the rotation direction of the motor. Activity 1. Solution. As it can be seen in the video, the fan attached to the DC motor changes direction in each loop after every 3 seconds. Please note that the speed of the DC motor was reduced to clearly show the change in direction in the video. Speed control of the motor will be explained in upcoming slides. Pulse width modulation, PWM. The concept of pulse width modulation, PWM, can be used to control the speed of a DC motor. But what is PWM? The concept of PWM is that while the signal from an Arduino can only be high, 5V, or low, ground, the ratio of time for which the signal is high to when it is low over a time interval can be used to change the effective voltage. It uses on-off or high-low signals of same frequency but varying on time. As it can be seen in the figure, the percentage of time for which the signal is high in one time period is called duty cycle. For example, a duty cycle of 25% implies the effective voltage applied as 0.25 times 5 volts, which is 1.25 volts. As the voltage supplied to a DC motor reduces, so does its speed. If the voltage is too low, that is, below the supply voltage required by the motor, it will not operate. Duty cycle. This formula can give a better understanding of the concept of duty cycle. Recall that the high signal from an Arduino is 5 volts. Pause in the video and give a thought about what duty cycle is required to get an effective voltage of 3.75 volts from an Arduino. The answer is 75%. Activity 2. DC motor speed control. Circuit. As shown in the slide, the circuit remains the same as that of Activity 1. Please note that the Arduino pins with a tilde sign next to the pin number are PWM pins, used to control actuators using PWM. Here, pins 10 and 11 is used to control a DC motor. Activity 2. DC motor speed control. Program. The only new line of code that was not introduced in Activity 1 is analog write. This command is used to write a value between 0 to 255. Here, it writes to the enable pin, which controls the PWM signal. For example, writing a value of 200 implies a duty cycle of 200 divided by 255, that is, 78%. An effective voltage of 3.9 volts, that is, 78% of 5 volts, which equals 3.9 V. In this program, the motor is supplied 3.9 volts for 4 seconds, then the supplied voltage is reduced to 2.15 volts for 4 seconds and then further reduced to 1.67 volts for 4 seconds, and back to 3.9 volts, and so on. Activity 2. DC motor speed control. Demonstration video. As expected from the program in the previous slide, this demonstration shows that the motor runs at almost full speed for 4 seconds, reduced to half the speed for 4 seconds, and runs at low speed for 4 seconds, and repeats the loop. Servo. A servo motor is a type of actuator, typically used for angular positioning. There are two major types of servos, standard servos and continuous servos. A standard servo typically has a movement range of 180 degrees, but the range can be more or less, based on the model. A continuous servo has a freedom to complete one full rotation and can rotate continuously, as it can be seen in the animation on the right. Standard versus continuous servo. Standard servo only turns over a range, usually 0 degrees to 180 degrees, with precise feedback control over its angular position, while a continuous rotation servo turns continuously, with control over its speed and direction. Standard servos are popular in robotic arms, while continuous servos are often used for wheeled robots. Servo. Sectional and exploded view. As you can see, a servo has a DC motor inside it and some other components for position feedback and control. Servo parts. Servo motors are constructed out of basic DC motors, but in addition to the motor, there is gear reduction, position sensor for the motorshaft and an electronic circuit that controls the motor's operation. Servo connector. A servo motor has a connector for 3 pins. The black wire is for the ground, the red wire for the power supply and the white wire for the signal. More often than not, if the servo is not working at all, odds are the connections to the servo are not in the right order. This is a common mistake. Interfacing Arduino with servo. Recall that the pins with tilde sign next to the pin number are PWM pins used to control a servo using PWM. In the diagram shown, pin 9 is used to control the servo. You will need to build this circuit for activity 3 in the next slide. Pause the video here to do this activity and hit play when you are done. Activity 3. The first line of the program is to include the servo library. The second line created a servo object named myServo. Then, an integer-type variable names, pos, is declared and initiated to 0. In the setup, pin 9 is attached to the servo object created. In the loop, two for loops are written. The first for loop is to move the servo from 0 to 180 degrees in increments on 1 degree, and the other, for loop, to do the opposite, that is, to move the servo from 180 degrees to 0 degrees in increments on 1 degree. A 15 milliseconds delay is given in each iteration of both the for loops, to wait for the servo to reach the desired incremental position. Activity 3. Demonstration. As it can be seen in the video, the servo moves from just 0 to 180 degrees. This is because the for loop in this case is written in the setup. Try implementing this circuit in all of the following iterations of the program. Just one for loop in the setup. Both for loops in the setup. Just one for loop in the infinite loop. Both for loops in the infinite loop. Observe what happens and try to correlate the program to what is happening with the servo. Pause the video here, attempt this activity and hit play when you are done. Continuous servo. This is for continuous rotation servo, not to be confused with the standard servo used in the previous activity. Wiring is same for both standard and continuous servos, since the connector is the same. In fact, unless labeled, one may not be able to see the difference between a standard and a continuous servo from the same manufacturer. Alternatively, to figure out the type of servo, it can be interfaced with a microcontroller and a program can be executed to check whether the servo stops after rotating to the angle in the program or not. If it does, it is a standard servo. If it rotates continuously, it is a continuous servo. As you can see from the PWM signal that at 1500 microseconds, the continuous servo does not move. For a high signal of duration 1300 microseconds, the continuous servo rotates clockwise at full speed, and for a duration of 1700 microseconds, it rotates counterclockwise at full speed. As the value OD duration is closer to 1500 microseconds, the speed reduces in both clockwise, less than 1500 microseconds, and counterclockwise, greater than 1500 microseconds, conditions. Note that here, the pulses repeat every 20 milliseconds, which is the delay given for the servo to respond to the signal before getting the next high signal. Motor considerations. Speed. While selecting a motor, there are some considerations based on the application. For example, the requirement could be to reach a certain point as fast as possible, that is, at high speed. It makes sense to use a high-speed motor in this case. More speed requires more voltage. As evident from the tabulated comparison, a high-speed motor requires more voltage. This information can be obtained from the datasheet provided by the manufacturer. It can be found by searching online using the part number. Watch the video on the right that compares a high-speed and an ordinary servo from Parallax. Motor considerations. Torque. On the other hand, the requirement could be to carry a certain load, which would require high torque. It makes sense to use a high-torque motor in this case. More torque requires more current. As evident from the tabulated comparison, a high-speed motor requires less current compared to an ordinary servo, which has higher torque. Recall that this information can be obtained from the datasheet provided by the manufacturer. Watch the video on the right that compares the torque capacity of a mobile robot operating using high speed and an ordinary servo, which has higher torque than a high-speed servo. The high-speed version cannot counter an obstacle on its way, but the higher torque version can keep going, and moves the obstacle along with it. Challenge activity. Control servo motor using potentiometer and 3 different colored LEDs to glow at 0 degrees, 90 degrees and 180 degrees. Pause the video here to attempt this challenge and hit play when you are done. Challenge activity. Solution. This is a demonstration video for servo control using potentiometer and indication using different LEDs when the servo header reaches 0 degrees, 90 degrees and 180 degrees. Challenge activity. Solution. Circuit. This circuit schematic shows the breadboard connections and interfacing of the potentiometer, LEDs, and servo with the Arduino. A common mistake is to forget the common ground. Try checking that first while troubleshooting, if required. Challenge activity. Solution. Code. The program for this activity is quite simple. It is a combination of 3 activities that have already been introduced. Turning an LED on or off, reading potentiometer, and controlling the angle of a standard servo. The portion of the code shown in this slide has integer variables with meaningful names declared for the pins connected to the respective components and created a servo object. In the setup, the LED pins are set to output mode and the servo pin is attached to the servo object. In the infinite loop, all the LEDs are set to low first, that is, turned off. Then the value of the potentiometer is read using analog read command and mapped to the range of 0 to 180, since that is the range of servo angle rotation, in this case. Then, this mapped value is written to the servo which results in the control of servo angle using the potentiometer. Lastly, the value is checked to decide which LED should be turned on. Ideally, the value would be compared to 0, 90, and 180 in the if statements with a double equals sign. But there is an issue due to human instability in holding the potentiometer dial at a certain exact position and the potentiometer is not very precise. For example, at 90 degrees, the LED turns on when the servo value is exactly at 90 degrees, which is not very evident, and the LED keeps flickering. By trial and error, close enough greater or less than comparisons were used. For example, instead of comparing the value to 90, it is checked if the value is between 80 and 110. Task. Activity. At this point you should be familiar with the following concepts were from the activities in this lesson. Find duty cycle and power, when PWM on time is given. DC motor direction control for 2 motors. DC motor speed control for 2 motors. DC motor speed and direction control for 2 motors. Servo motor angle control, user input. Rotational servo motor calibration. Rotational servo speed control. Rotational servo motor direction control. Thank you.